Before we can explore the details of how computer systems operate, we need general knowledge of the structure of a computer system. In this section, we look at several parts of this structure. So, first part, computer system operation. A modern general-purpose computer system consists of one or more CPUs and a number of device controllers connected through a common bus that provides access to shared memory. Such as this picture, this is CPU, this is memory. All others here, all others are I/O devices. Okay. So, each device controller is in charge of specific type of device. For example, disk drives here, disk drives, audio devices, or video displays. The CPU and device controllers can execute in parallel, competing for memory cycles. To ensure orderly access to the shared memory, a memory controller synchronizes access to the memory. Of course, in this picture, no memory controller. Okay, it doesn't draw it. Okay, and for a computer to start running, for instance, when it is powered up or rebooted, it needs to have an initial program to run. This initial program or bootstrap program tends to be simple. Typically, it is stored within the computer hardware in read-only memory or electrically erasable programmable read-only memory, known by the general term firmware. It initializes all aspects of the system, from CPU registers to device controllers to memory contents. The bootstrap program must know how to load the operating system and how to start executing that system. To accomplish this goal, the bootstrap program must locate the operating system kernel and load it into memory. Once the kernel is loaded and executing, it can start providing services to the system and its users. Some services are provided outside of the kernel by system programs that are loaded into memory at boot time to become system processes or system daemons that run the entire time the kernel is running. On Unix, the first system process is init, and it starts many other daemons. Once this phase is complete, the system is fully booted, and the system waits for some event to occur. The occurrence of an event is usually signaled by an interrupt from either the hardware or the software. Hardware may trigger an interrupt at any time by sending a signal to the CPU, usually by way of the system bus. Software may trigger an interrupt by executing a special operation code, a system call, also called a monitor code. When the CPU is interrupted, it stops what it is doing and immediately transfers execution to a fixed location. The fixed location usually contains the starting address where the service routine for the interrupt is located. The interrupt service routine executes. On completion, the CPU resumes the interrupted computation. A timeline of this operation is shown here. Okay, is shown here. Interrupts are an important part of a computer architecture. Each computer design has its own interrupt mechanism, but several functions are common. The interrupt must transfer control to the appropriate interrupt service routine. The straightforward method for handling this transfer would be to invoke a generic routine to examine the interrupt information. The routine, in turn, would call the interrupt-specific handler. However, interrupts must be handled quickly, since only a predefined number of interrupts is possible. A table of pointers to interrupt routines can be used inside to provide the necessary speed. The interrupt routine is called directly through the table, with no intermediate routine needed. Generally, the table of pointers is stored in low memory, that is the first 100 or so location. These locations hold the addresses of the interrupt service routines for the various devices. This array or interrupt vector of addresses is then indexed by a unique device number given with the interrupt request to provide the address of the interrupt service routine for the interrupting device. Operating system is different as Windows and Unix dispatch interrupts in this manner. The interrupt architecture must also save the address of the interrupted instruction. Many old designs simply store the interrupt address in a fixed location or in a location indexed by the device number. More recent architectures store the return address on the system stack. If the interrupt routine needs to modify the process state, for instance, by modifying register values, it must explicitly save the current state and then restore that state before returning. After the interrupt is serviced, the saved return address is loaded into the program counter, and the interrupted computation resumes as though the interrupt had not occurred. Storage structure. The CPU can load instructions only from memory, so any programs to run must be stored there. General-purpose computers run most of their programs from rewritable memory, called main memory. Main memory commonly is implemented in a semiconductor technology called dynamic random access memory. Computers use other forms of memory as well. We have already mentioned read-only memory and electrically erasable programmable read-only memory. Because ROM cannot be changed, only static programs, such as the bootstrap program described earlier, are stored there. The immutability of ROM is of use in game cartridges. EEPROM can be changed but cannot be changed frequently, and so contains mostly static programs. For example, smartphones have EEPROM to store their factory-installed programs. All forms of memory provide an array of bytes. Each byte has its own address. Interaction is achieved through a sequence of load or store instructions to specific memory addresses. The load instruction moves a byte of word from main memory to an internal registers within the CPU. whereas the store instruction moves the content of a register to main memory. Aside from explicit loads and stores, the CPU automatically loads instructions from main memory for execution. Okay. Ideally, we want the programs and the data to reside in main memory permanently. This arrangement usually is not possible for the following two reasons. One, main memory is usually too small to store all needed programs and data permanently. Second, main memory is a volatile storage device that loses its contents when power is turned off or otherwise lost. Thus, most computer systems provide secondary storage as an extension of main memory. The main requirement for secondary storage is that it be able to hold large quantities of data permanently. The most common secondary device is a magnetic disk, which provides storage for both programs and data. Most programs are stored on a disk until they are loaded into memory. Many programs then use the disk as both the source and the destination of their processing. Hence, the proper management of disk storage is of central importance to a computer system. In a large size, however, the storage structure that we have described, consisting of registers, main memory, in a larger sense, however, the storage structure that we have described, consisting of registers, main memory, and magnetic disks, is only one of many possible storage systems. Others include cache memory, CD-ROM, magnetic tapes, and so on. So this picture, okay, register, storage device hierarchy. Okay. The main differences among the various storage systems lie in speed, cost, and volatile. Okay. The wide variety of storage systems can be organized in a hierarchy according to speed and cost. The higher levels are expensive, but they are fast. As we move down the hierarchy, the cost per bit generally decreases, whereas the assigned time generally increases. This trade-off is reasonable. If a given storage system were both faster and less expensive than another, other properties being the same, then there would be no reason to use the slower, more expensive memory. In fact, many early storage devices are relegated to museums now that magnetic tape and the semiconductor memory have become faster and cheaper. The top 4 levels of this memory picture may be constructed using semiconductor memory. That means registers, cache, main memory, electronic disk, that we also call it solid-state disk, are constructed by semiconductor. Okay. In addition to differing in speed and cost, the various storage systems are either volatile or non-volatile. As mentioned earlier, volatile storage loses its contents when the power to the device is removed. In the absence of expensive battery and generator backup systems, data must be written to non-volatile storage for safekeeping. In hierarchy of this picture, register, cache, main memory are volatile, memory. And the electronic disk, magnetic disk, optical disks, and magnetic disks are non-volatile. Solid-state disks have several variants. The design of complete memory system must balance all the factors just discussed. It must use only as much expensive memory as necessary while providing as much inexpensive non-volatile memory as possible. Caches are be installed to improve performance when a large disparity in access time or transfer rate exists between two components. I/O structure. Storage is only one of many types of I/O devices within a computer. A large portion of operating system code is dedicated to managing I/O, both because of its importance to the reliability and performance of a system, and because of the varying nature of the devices. A general-purpose computer system consists of CPUs and multiple device controllers that are connected through a common bus. So, this picture, disk controller, USB controller, and graphics adapter. They are all device controllers. Each device controller is in charge of a specific type of device. Depending on the controller, more than one device may be attached. For instance, 7 or more devices can be attached to the small computer system interface controller. We also call it a SCSI controller. A device controller maintains some local buffer storage and a set of special purpose registers. The device controller is responsible for moving the data between the peripheral devices that it controls and its local buffer storage. Typically, operating systems have a device driver for each device controller. This device driver understands the device controller and provides the rest of the operating system with a uniform interface to the device. To start an I/O operation, the device controller loads the appropriate registers within the device controller. The device controller in turn examines the contents of these registers to determine what action to take. The controller starts the transfer of data from the device to its local buffer. Once the transfer of data is complete, the device controller informs the device driver via an interrupt that it has finished its operation. The device driver then returns control to the operating system, possibly returning the data or a pointer to the data if the operation was a read. For other operations, the device driver returns data's information. This form of interrupt-driven I/O is fine for moving small amounts of data, but can produce high overhead when used for bulk data movement, such as disk I/O. To solve this problem, DMA is used. After setting up buffers, pointers, and counters for the I/O device, the device controller transfers an entire block of data directly to or from its own buffer storage to memory with no intervention by the CPU. Only one interrupt is generated per block to tell the device driver that the operation has completed, rather than the one interrupt per byte generated for low-speed devices. Where the device controller is performing these operations, the CPU is available to accomplish other tasks. Some high-end systems use switch rather than bus architecture. On these systems, multiple components can talk to other components concurrently, rather than competing for cycles on a shared bus. In this case, DMA is even more effective.